start. All right. Welcome to, I guess as somebody put it last time, Hump Day. So it's the middle of the week, and we're sort of in the middle of our discussion of synchronization. So today we're going to try to get you through at least a few more of the synchronization primitives. And one of the things I like is that people are already sort of, do you guys have a contribution you want to make to the class? Okay. Yeah. It's just that when I get to talk, I've been waiting for like all Tuesdays. Oh, it's my chance to blather meaninglessly in front of a large group of people. No, just kidding. All right, so today we'll finish talking about spin locks, and then we'll get into how you use these spin locks to build more interesting and useful synchronization primitives, including some of the primitives that you guys are experiencing as part of assignment 1. How many people have started assignment 1? Awesome. That's good news for you guys. Yeah, cool. So yeah, we're seeing assignment 1 questions during office hours. That's awesome. I think next week we're going to start moving the recitations forward to assignment 2 because we just won't have enough time to get through that to give you guys enough time to do the assignment if we don't. So, all right. Let's see here. All right, so based on the Piazza poll, I think after break is the overwhelming choice for the exam. You guys may think this is great, but then you're going to be, lying on some beach in Tahiti, and you're going to be like, oh man, like operating system concepts will be running through your mind, and it'll be like kind of sad. So anyway, but you guys did this to yourselves. Don't blame me. That will give us a chance to cover a little bit more material, which is good. So that's nice. Finally, there are some people in the class who, for one reason or another, are working by themselves on the assignments. If you think you fall into that category, please email the course staff as soon as possible so that we can make sure that we know that you're working alone, and then we can set up things so that you have a portion of the assignments that you can complete, and we don't expect you to do the work of 2 full-strength 421, 521 students. All right. So any questions about Monday's talk? So on Monday we talked about critical sections, and we started to sort of motivate the need for new tools to enable synchronization when we start using multiple threads. Any questions about Monday's stuff before we plunge onward? All right. So the illusion of concurrency, right? So we've created this notion of threads, and this was great, right? This is a powerful illusion. What else is it, though? Both powerful and what? Powerful and useful, right? This is a way of keeping the CPU fully engaged, and it's also a great way of thinking about how to structure our programs, right? And also sort of dealing with the latencies caused by hardware devices, which is sort of part of the process of keeping the CPU engaged, right? We want to keep the CPU busy, so when the CPU needs to wait for something, we can find something else to do, right? This is great. Unfortunately, we start talking about the problems this creates on Monday, right? So what's one of the problems created by the illusion of concurrency? Matt? Yeah, so one of the problems is race conditions, but what's the underlying issue here, right? There's 2 things that we want to enable, 2 properties, yeah. Yeah, so we want to enable some kind of coordination, right? We need to build mechanisms, particularly in the kernel, to allow multiple threads to coordinate with each other to accomplish some common goal. And then what happens when we don't get this coordination quite right? What's the other goal of the synchronization primitives?
Cooperation.
Yeah. Correctness. It's another co-word, right? Anyway, I just had a random aside, but I'm not even going to talk about it. This has to do with double O's on letters like this. So, right. So coordination and then correctness, right? So how do we make sure that when the illusion of concurrency causes threads to be stopped and started at any time, certain types of shared state are manipulated in a way that's correct, right? And we introduced this idea of atomicity, right? It's sort of another type of illusion that can be created by the kernel. So concurrency what's the illusion of concurrency? On a uniprocessor system, the illusion of concurrency is simply that, yeah, that multiple things are happening at the same time, despite the fact that in reality only one thing is running on the system, right? And once you have multiple cores, you can sort of extend this idea naturally, right? In contrast, what is atomicity? Yeah.
It looks like separate things are happening all at once.
Yeah, I love that you come in from there. It's like, I just started waiting for this little surprise. Yeah, sweet. It's like a big entrance. I should do that one day in the wander. Yeah. So atomicity. Atomicity is the illusion that a bunch of things that actually happen separately happen at the same time, right? That's what we talked about when we talked about something being atomic, right? An atomic operation. It's indivisible, right? It cannot be observed in a divided state from the outside, right? So what assumptions do you have to make now in your new brave life as a multi-threaded programmer? When you start writing threads, what are the assumptions that you have to make unless you do something about it? Damien. Yeah, so the threads could, first of all, the threads could run in any order, right? You can't make any assumptions about how the scheduler is going to schedule your threads, right? They can be stopped and restarted at any moment. You can be in the middle of doing something and you can be whisked off the CPU. Somebody else can run, and then later you'll get a chance to run again. And by that point, things may be different, right? And once you're stopped, you could remain stopped for arbitrary lengths of time, right? So unless you do something about it, you have to start living with these new realities. We talked about critical sections, right? Critical sections gave us this ability to create an atomic block of code, right? There was atomic with respect to other threads that were trying to use that same function or enter that same block of code. And here were the design requirements, right? Mutual exclusion, making sure that when I have a critical section, only one thread can be inside the critical section at one time. I also want to make sure that all threads are eventually allowed to progress through the critical section, and this happens relatively quickly. And one of the ways we do that with critical sections is making the critical sections short, right? When you guys start working on assignment 3, something that's you'll start to deal with is the fact that when the kernel blocks inside of one of these critical sections, right? So what's one way to keep your critical section short? If you have this general design principle of keeping the critical section short, I mean, clearly you can keep them short in terms of lines of code. That doesn't always work. What should you avoid doing inside a critical section? Yeah, James.
Function call?
Oh, you can make a function call. Function call is not so bad, as long as that function call doesn't do what, Natasha?
Make context switch.
Well, you could be context switch, and something else could run. You come back to the critical section. I mean, it's always short with respect to other people who are trying to use the critical section. Yeah. Oh, you could do that too. That might be fast. Yeah, Nishan.
Avoid spinning?
Oh, you could be spinning as long as you're doing some work. Yeah.
Use anything that'll take a long period of time.
Yeah, like what? Like use some slow device, right? If you use a slow device inside a critical section, it might just be one call, right? You might be like, yeah, my critical section was only one line. It was read, right? And now your critical section has gotten really, really long, right? So avoid blocking inside a critical section. All right, so critical section is this idea that there's one block of code that only one critical section can be inside, one thread can be inside. And again, the critical sections look atomic with respect to other threads that are outside the critical section. Right? So if you keep your manipulations to certain shared data structures inside critical sections, then those manipulations will look atomic with respect to other people who are using the resource. Right? So we talked a little bit about how on multi-core systems in particular, we actually implement some of these concurrency primitives, and it relies on some form of hardware support, right? And there were two types of hardware, low-level hardware support that we talked about. One was this idea of something that performs a test and set, right? And then something else that performs a compare and swap, right? And variants of these are provided by most modern architectures to deal with these types of synchronization issues. Yeah?
What exactly is test and set? Like, why would we test and set?
Why would we test and set something? Let's use that in our example, which we're about to do, finish from last time, and then I'll come back to your question. Does that make sense? I will show you what we will do with the test and set in a minute. All right? Okay. All right, so let's get back to our, well, actually, sorry, this got inside and this is outside. So any questions about this material before we finish the example, right? So remember, we were in the process of modifying this sort of contrived example about my account balance to make it safe by using a low-level sort of hardware-esque synchronization primitive, particularly use a test and set, right? And here was our first attempt, right? So here's the critical section that we identified last time. It's the part where I'm manipulating the account balance, which is the shared state. And here is my call to set the test and set, right? So essentially, I'm using the variable that's protected by the test and set as simply as an indication of whether or not there is a thread that is, sort of busy inside this critical section, right? So when I enter the critical section, I set it to 1. That tells other threads, hey, I'm inside the critical section right now. And when I leave, I set it to 0. And we decided that this worked fine.
No.
No, right? Because remember, only one thread is supposed to be inside the critical section at one time. So if thread A runs this and is right here and gets context switched, thread B is just going to go right through, right? There needs to be some, we need to do something to keep thread B out of the critical section, right? Does anyone remember there were 2 ways that we could keep other threads out of our critical section? This goes Monday review. Yeah. Yeah, so if I can prevent other threads from running, now, does this work anymore? Has this worked since like 1992, roughly? No, because most of the time now machines have multiple cores, right? And I don't want to shut down every core in the system just so I can run, right? And usually that's not even necessarily that easy to do, right? So what was the other alternative? I can't keep other threads from running, right? So I need to stop them before they get inside, right? The other thread has to halt there and wait for me to finish, right? And so here is one way of doing this, right? So here's my test and set right here. And what does this do? So what does this loop do? So while the test and set returns 1, well, what is this? If I wrote this loop of code, what would it actually do? What would be the next thing it would do? Yeah, it would keep asking again. It's like it's keeping banging on the hardware, being like, is it 0? 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 Right? And this would actually work. Okay, right? And all I do is I just go back and check it again, over and over again. As soon as this returns 0, right, I'm going to break out of the loop. But why is this safe to do, right? What if there are 2 threads that are spinning on this test and set, and one thread's inside the critical section, and then it leaves? What does the test and set guarantee?
Only one thread changes the value.
Only one thread will see 0, right? The next one will just see 1 again, and it'll keep spinning. So this works, right? This will actually work. What's the problem with this, though? There's a couple of problems with this approach, actually. What's one problem? Yeah.
Should waste a lot of CPU cycles because a lot of threads are spinning on the same and checking the variable again and again and again.
Okay, so in the bad case, the just bad case, this wastes a lot of processor time, right? Because, let's put it this way. While, let's say I have a single processor system. What cannot happen while one thread is spinning on the test and set? It can't change, right? Like, I'm running, this guy is sleeping, and I'm just, I'm essentially running an infinite loop, right? And the only way it's going to change is if I stop doing that and let that other guy run. Now, if you had also prevented the scheduler from running, you had disabled interrupts and you were spinning on this, then what could happen? Then just your life is over, right? Like, your kernel is going to spend the rest of its life waiting for the stupid test and set to change, right? And it never will. And nothing else will ever get to run, so it never will, right? Where would this be more useful, right? So that's particularly the case usually on a uniprocessor system, right? But on a multiprocessor system, how do the assumptions that we just made change? What could happen on a What could happen on a multiprocessor system that would mean that it might be a good idea to spin on the test and set? Remember, on a single processor system, as long as I'm checking the test and set, nobody can change it. What about on a multi-core system? Yeah?
Another thread can come inside and change the test and set value.
Yeah, another thread might be running on another core, and it might actually drop the test and set while I'm spinning, right? So it's possible on multi-core systems that this is OK to spin for a little while, because unless the thread that's trying to run is on my core for some reason and I'm preventing it from running, it might be running on the other core, right? So this form of sort of providing access to resources is called busy waiting, right? So essentially, this is kind of just sitting there pounding on the door waiting to get the resource, right? And what it means is while I'm waiting for the resource, I'm keeping the system busy, right? And again, this is not necessarily great on a multi-core system, but it can be very bad on a single core system in certain cases, right? So here's how this would look with the example we were using, right? Thread 1 runs, it gets the lock, it enters the critical section, it sets the test and set to 1, and then maybe it gets context switched, or this is happening simultaneously on another core, but the other thread just sits in here checking the test and set, right? So you can imagine how this works, right? So now all of this has essentially wasted effort, right? These are cycles that the processor consumed without really doing any useful work, all right? So in order to solve the problem with these spinning locks, right, we're going to talk about a more general primitive, right? But this is really, what we've really built is an example of something that's called a lock, right? And locks are a pretty intuitive synchronization primitive to think about, right? Locks essentially give somebody exclusive access to a particular resource. And locks can be used to implement critical sections. So to implement a critical section using a lock, when you enter a critical section, you acquire the lock. And when you release it, when you leave the critical section, you release the lock. So you're essentially using a lock to make the portion of code that you're executing into a resource that only one thread can acquire or release at the same time, right? Now, what we've implemented so far is what's called a spin lock, right? Lock, for the fact that this is used to guard a critical section or provide exclusive access to a resource. Well, today is Wednesday, so I guess that'll be Friday, or maybe hopefully today. And spin describes the process of acquiring a spin lock, right? I busy wait. I continue to spin repeatedly on the lock, hoping that it is going to become available. And one of the reasons we're asking you guys to build new synchronization primitives for assignment 1 is that spin locks are rarely the right solution to a synchronization problem. But they are frequently a primitive that other synchronization primitives use, right? They're a tool. And you guys how many people looked at the semaphore implementation? So you've seen a case where spin locks are used in order to implement a different kind of synchronization primitive, a synchronization primitive that does not use busy waiting, right? And spin locks of this type that use these underlying hardware features are particularly important on multi-core systems, right? To provide these types of synchronization primitives, right? All right, so let's modify our example before, right? To instead of using this sort of really ugly low-level hardware resource, let's just implement it using a lock type interface, right? So how do I change this example to do that? Remember, locks have two functions that matter: acquire and release. Where do I put the acquire? Where do I put the release? Damien, where do I put the acquire? Yeah, so and here's how to use a lock. I'm going to identify the critical section, which we did, and then we lock around it, right? So here's where the lock acquire goes. Where do I release the lock? Yeah. Yeah, we couldn't decide before where this really had to be, right? But identify the critical section and then lock around it, right? So I acquire the lock and release the lock. I also need, some sort of lock structure to use here, right? So this is an example of how to use a lock to protect this critical section. Any questions at this point before we keep going? Yeah.
What's the difference between test and set in this? In both the cases, it's more or less a Boolean that we either require or release or.
Yeah, so you could use, so someone has noticed that I've just played a little trick. You could use the test and set approach that we just developed to implement this lock, right? But what you're going to do in assignment 1 is you're going to implement locks in a more intelligent way that don't busy wait, right? And there are some interesting design trade-offs between the two type of locks, right? And here's an example of one of them, right? So the semantics of the lock interface require that I wait. When I try to acquire a lock, that call will block until I have exclusive access to the resource. And so we talked about one way of implementing this, which is this active busy waiting model, right? Where I repeatedly spin using some sort of low-level synchronization primitive, or I could just use spin lock on OS 161 to acquire the lock. And that's this active or busy waiting. What's the other alternative? Yeah.
Put the thread or whatever, trying to try to leave it sleep until the lock no longer needed.
Yeah, so a better way to do this in many cases, in most cases, is to get out of the way, right? If I acquire a lock and the lock is busy, the lock is held, the best thing for me to do in most cases is stop executing so some other thread can continue working, right? If I go into the waiting state, if I call thread yield, if I get out of the way, it's much more likely that whatever thread is inside the critical section will be able to finish what it's doing, leave, and allow me to enter, right? And this is this form of what's called passive waiting, right? This involves, and this involves a little bit more work than active waiting, right? I have to have some way of telling the system, the kernel, or whoever's providing the lock implementation, here's what I'm waiting for. And then I need some mechanism for actually sleeping, right? And then some mechanism for awakening threads once lock release is called, right? Luckily, on your system, you guys already have these mechanisms in place, right? You just have to figure out how to use them correctly. So again, there are a couple of interesting cases where spinning is actually the right thing to do, right? So again, I've made it sound like, sleeping is a far superior approach, right? I mean, if I try to get a lock and the lock is held, I should just go to sleep and then, rely on someone to wake me up when somebody leaves the critical section and I can reacquire the lock. What do you think is one case where spinning might be more effective? Yeah.
Anytime it's a really short critical section.
Yeah, so when my critical sections are really short, spinning might be a better idea. Why? Yeah, Scott. Yeah, so remember, sleeping requires a context switch. So if I go to sleep, let's say the critical section is only a couple of instructions long, right? And I checked it, and I just happened to check it at the exact moment somebody else was inside. And now I'm executing the hundreds of instructions potentially to go to sleep. And by the time I actually get to the wake queue, then that other thread has exited, and now I just get woken up immediately, right? So now I've done both an unnecessary sleep and an unnecessary wake up. So when the critical sections are really short, right, then it's possible that spinning is better, right? And again, only on multi-core systems would you ever do this, right? Because on single-core systems, nothing will change until I allow another thread to run. But if the critical section is short on a multi-core system, there are cases when spinning can be the right approach, right? And here's another case where I want to make sure that we incorporate this idea that context switches are not free, right? There's an overhead to stopping and restarting execution. Yeah.
Is it important that we know these kind of quirks of both single and multi-core systems, or should we focus on understanding?
Yeah, I don't know. I'm a relic of the single core era, right? Don't repeat my mistakes. I think I would just focus on multi-core systems, right? Because there's really, yeah. And I apologize for some of the stuff on here. I mean, some of the concepts here are legacies of the days when we had single core systems. But really, if you want to do anything safely, think about multi-core, right? And really think about multi-core almost exclusively. Right, so here's this sort of silly example. All right. So most kernels provide some type of functionality allowing threads to wait for something, right? And frequently this is based on some sort of key, right? So, this you guys have an equivalent mechanism in your own kernel. It essentially says, dear kernel, I'm going to sleep, but there's something I'm waiting for, right? And when that thing happens, please wake me up, because it's possible I'll be ready to run again. We're talking about this in the context of synchronization, when the wake-up event would be generated by what, right? With locks, what generates the wake-ups? Release, right? So release is the moment where the kernel will go through the threads that are sleeping and try to figure out who is waiting for that lock. But where else would this be used? This is a more general purpose mechanism than just for synchronization primitives, right? What other times would threads in the kernel sleep? Yeah. Yeah, anytime I perform some hardware operation, right? I'm waiting for the disk read to complete, right? I go to sleep, right? I'm certainly not going to busy wait on a disk. And I allow the kernel to wake me up again when the operation is complete, right? So this is sort of the underlying mechanism that's used. And again, these things are not limited to the kernel, right? You are a lot of user space threading libraries and most programming libraries at this point. I mean, again, if you want to do anything interesting with your system, you're going to be using multiple threads. And for that reason, you know, any good threading library provides a lot of this functionality, right? Because it's important, right? All right, so locks, yeah.
In the previous slide, when you were
Yeah.
saying key, is that kind of like a condition variable?
No, the key here is the key here is really just an abstract key, right? Some identifier, right? For I don't know. I'm trying to think. I mean, for a lock, it could be some state in the lock that identifies the lock from other locks. When I'm doing requests for the disk, I probably need some way of identifying the request so the kernel can tell when it's finished, right? But yeah, the key here is like the I don't know what the right word is, like the sort of a, anyway, my brain is failing me. It's a very abstract key, right? Good question. Any other questions about locks? All right. So locks are designed to protect these critical sections, but remember we talked both about ways, you know, the two goals of synchronization, right? Correctness, which locks can help you achieve, but also coordination, right? And coordination between threads frequently requires some kind of communication mechanism, right? So locks are designed these critical sections, and you can think to some degree of lock release as a signal, kind of. It's not, and I don't mean signal as in the signals that the operating system sends processes. I mean signal is a form of communication, right? A way of the thread that's leaving the critical section telling other threads, hey, the critical section is available, but it's not really that useful as a communication mechanism for enabling coordination, right? But there's lots of other times when I'm trying to write multi-threaded programs that I want to enable some kind of synchronized communication between threads, right? And so here's some examples of these, right? So for example, if I have a buffer where I have both producers that are putting items into the buffer and consumers that are pulling them out and doing something with them, the producers might need a way to tell the consumers, hey, there's data in the buffer. Pretty easy. For assignment 2, you guys will have fun with this one, right? The parent needing, or the operating system needing to be able to notify the parent, your child is exited, right? That's another, and usually the notifying thread here is the child, right? As the child as the child exits, he wants a way to make sure to notify the parent that it's exited, so the parent can collect its status, right? And condition variables, and unfortunately, condition variables have this terrible name, right? Which is really, really incredibly misleading. And I think in order to understand condition variables, the way to do it is sort of eliminate the variable from the name, right? Condition variables don't have, there's no concept of a variable. There is usually a variable associated with a condition variable, but that variable is not inside the condition variable. That variable is outside the condition variable, right? So for example, with these two, get on the slide, with these two examples, right, the condition, right? So what's the condition here for the first example? I have a producer-consumer problem, buffer that's shared that people are putting items into and retrieving them. But what's the condition that a condition variable would be designed to express? Yeah, what's the state of the buffer? Is it empty? Is it full? You know, or is it somewhere in between, right? But usually empty and full, right? Because empty and full have special implications for the producers or the consumers, right? If the buffer is empty, the consumers don't have any work to do. If the buffer is full, the producers have to wait, right, to put items into it. Same thing with the child exited. I think I come back to this. You know, here I could express, and again, the condition is usually represented outside of the condition variable as some condition based on shared state, right? So if the buffer has data in it, then the consumers can take items out of the buffer. If the buffer is full, then the producers cannot produce into the buffer, right? Yeah, and so let me go back to this. So the CB interface, which you guys have started to look at, right, is there are 3 calls, right? There's wait, there's notify, and there's signal. And really, you can think of this as the CV interface, if you guys have looked at the OS161 code, looks a lot like the wait channel interface, right? There's a way to wait, and normally that wait is done in the context of waiting until something becomes true. That's not actually required by the condition variable, right? There's notify, and then there's signal, right? So what will happen is notify will wake up, I'm trying to remember, will wake up, is it one thread or all the threads? I always get these backwards. Notify is one? All the threads, right? Okay, so signal is one, right? And notify is all of them. So the idea here is when I call CV wait, I will sleep until another thread calls either CV signal or CV notify. Yeah, James.
It's the one to wake up all of them. It's actually called broadcast.
I think it's called broadcast in your systems. Yeah, okay. It's a bug, another bug on the slides. And that makes more sense, right? Broadcast will cause all the threads that are waiting on a particular condition to wake up, right? Now remember, the condition variables are entirely a signaling mechanism on your system. There's no condition inherent to them. So when a thread wakes up after calling CV wait, the first thing it does is usually look at the condition again, right? So for example, if I'm I think I have an example here, right? Yeah, here we go. So this is let me see if I actually get to the producer. Oh, I think I did a producer-consumer example. I think it's in the next lecture, right? So the condition usually is expressed as some sort of operation on the shared state, and it can, it indicates some change that the threads that are waiting on the condition are interested in, right? So if I'm the producer and the buffer is full, I have to wait, right? So with the producer-consumer example, there are two cases where I have to wait. One is if I'm the producer and the buffer is full. What's the other condition? If I'm the consumer and the buffer is empty, right? So, if the buffer is full, I can let threads withdraw items but not add items. If the buffer is empty, I can let them add items, but there's no work to do, right? So I can't let them withdraw, right? And if the buffer is in between those two states, then no one really needs to wait, right? But the condition, the CV variable allows threads to signal each other when these things happen. So let's say I'm a producer and I see that the buffer is full. Go back to the CV interface. What would I do? I call CV wait, right? Because I'm waiting for a change in the condition, right? The condition is the state of the buffer. Who would wake me up? Yeah, a consumer, right? So when a consumer withdraws an item from the buffer, it would want to say, hey, all the producers that have been waiting for the buffer to have room in it, now there's room in the buffer. We'll go through an example of this next time, which will make this more concrete. All right, let me get through semaphores, and then we'll have sort of covered all of these useful synchronization primitives, right? So semaphores are essentially a synchronized shared counter. I know this, man, I should have put examples throughout these rather than trying to do them all in one slide, right? Semaphores provide an interface to access a shared counter with synchronized sort of increment and decrement operations, right? That's pretty much all semaphores are, right? This interface, the P and B interface, do you remember who you guys have to thank for that? Dijkstra, right? These are, there's some Wikipedia article you could look up that sort of will tell you what these are stand-ins for, right? But V, or you can think of as up, will raise the value of the counter, and P will decrement the counter by 1. There's only one little wrinkle here, right? If you had this kind of abstraction, it might be kind of useful, right? Just because it synchronizes access to the shared counter. But how else could I synchronize access to a shared counter? Let's just say I had a variable, and I wanted to make sure that if two threads both incremented at the same time, it ended up being 2 rather than 1. What would be another way of doing that using the synchronization primitives we've already talked about? I could use a lock, and maybe even use a spin lock. It's a short operation, right? But I could certainly use a lock to protect access to that variable, and that would work fine. The only thing that's different about semaphores is that if the value, if decrementing the value would cause it to go below 0, the thread that calls V will sleep, right? So the value of a semaphore can never go below 0. It can go as high as it wants to, right? Can never go below 0. And if I try to p a semaphore that's set to 0, I will wait. So and a binary semaphore is a semaphore you could think of as restricted to have values between 0 and 1. How this restriction is done can be done a lot of ways. I mean, one way is if you try to v the semaphore and it's 1, you could panic or throw an exception or something like that. But another way of thinking about a binary semaphore is just a semaphore that only has values of 0 and 1. So we could, and again, there's an interesting distinction between semaphores and locks that some of you guys are coming across as you start to work on assignment 1. And this is a common question in this class, which is, what's the difference between a binary semaphore and a lock? Right? I'm not going to give away the answer in front of the whole class, right? But I'll just point out this, which is that, remember our example from before where I protected this critical section using a lock, right? I had a call to lock acquire right here, and I had a call to lock release at the bottom of the critical section. I can take that code, those calls to lock acquire and lock release, and I can replace them with P's and V's on a semaphore. And this code works fine, right? However, I cannot take, if I took calls to lock acquire and lock release and they were correct, right? I could replace them with calls to P and V on a semaphore. And that semaphore would essentially function as a binary semaphore. It would never have a value above 1. However, I can't take semaphores and replace them with a lock. So if I use semaphores and I went through all your code and I tried to essentially take all the P's and V's on semaphores that you were using properly and replace them with calls to lock acquire and lock release, that would not work, right? And this is actually even deeper than just the question of there being a counter, right? There's some concept that locks have that semaphores don't. And I actually just realized that it's on the slides, but there we go. Right, so it's not on there anymore. OK, so semaphores, and in general, one of the reasons that we give you guys semaphores is semaphores are not super useful. In fact, you can write all of the rest of the code that you're going to write for this class and never use a semaphore. There is one place in the code where some of you clever programmers will find a use for a semaphore. And it's kind of exciting. It's like, ooh, wow, like I could use a semaphore. That's really neat. But it's not very common, right? Most of the time, you're going to be using locks and condition variables. Those are locks, really, more than anything else. Semaphores are not particularly sort of a common synchronization primitive to use. All right. OK, so the one of the things to keep in mind, I know we're going to finish a little early today, so that's kind of nice, is that most synchronization problems can be approached in a variety of different ways, right? And as you guys start thinking about the synchronization problems for assignment 1, it's important to recognize the fact that most of these problems can be solved with locks. Sometimes they can be solved with either locks or semaphores or locks or CVs or some combination of them, right? And it takes some practice to get good at choosing the right synchronization primitive to solve a particular synchronization problem, right? And this is something that we're going to give you some practice doing for assignment 1. And then for assignments 2 and assignments 3, you'll have plenty of other chances to use synchronization primitives as you go along. And this is just something that you'll get better at with practice. One thing to keep in mind is that if you start solving a synchronization problem and it starts to get really gross, and you're using like 4 locks, right? Or like 3 or 4 CVs, and stuff starts to feel really odd and weird, then it's possible that you should rethink your choice of primitive, right? Sometimes, if there is a way to solve the problem using like 18 semaphores, but that might not be the best way to do it, right? There might be a cleaner way to solve the problem using another tool. All right, so on Friday, and I wish I had timed this out a little bit better and had some of these up today, we will talk about some problems with synchronization primitives, specifically with locks. And we'll also go through some sample synchronization problems, right? You guys are welcome to leave. I'll also stay for 10 minutes if people have questions about stuff today. I think we went a little fast. So are there any questions about? Everyone just wants to run home and do assignment 1, which is awesome.